The other day, a student asked me if I could simplify the concept of the chain rule in calculus for them. I replied yes, provided you can do two things. One is to decompose a composite function, and the second is to know the basic rules of differentiation for elementary functions. For the next few moments, I will look at an example without giving formal proof. So let's take a look at function notation. I want to express a composite function. So let's say it has four pieces. So if I had a function that I could decompose into four pieces, I would express it like this, or in more conventional format, like this. If I want to express the derivative of this function in Lagrange notation, which is the prime notation, then I would write it as such. And you see the kind of pattern that emerges. It's kind of a nested pattern. And you'll see a kind of a chain pattern emerge when I use Leibniz notation. df/dh times df/dr times dr/dg times dg/dx. And if I can change pen colors, you'll see in the Leibniz notation, you'll see this kind of a pattern that emerges. I'm circling the elements here where the numerators and denominators of the differential terms are the same variable. Looks kind of like a chain pattern. So I don't know if that's where the chain rule got its name, but that's what conjures up in my mind a way to remember it. If I can decompose my function, then I should have a chain type pattern. So next I'm going to look at a specific example. I'm going to look at the function f of x equals the exponential of sine square root x cubed plus 2x. In order to do the chain rule, we need to decompose f into composite pieces. I do that by utilizing parentheses. So I'm going to now utilize parentheses. The exponential is a function. It will be operating on the sign. So I'm going to use my outer set of parentheses. The sign is a function, so I will use parentheses to denote that it's a separate function. Inside the sign, the argument of the sign function is a square root function, so I'll indicate that by another set of parentheses. And then finally, the most inner piece of the radical is another function. It's a polynomial. And so that's how I will write this function in with parenthesis notation, demarking those and identifying those particular functions. So now it becomes easy to decompose this function. I can let g represent the innermost, and that's what you always want to do, start with the innermost function that you have identified. And then I'm going to write r, using r for radical. So that's going to be the square root of g, which is equal to g to the 1/2 power. And then f, I'm going to let that represent the sine function. With this substitution, this is the sine of r. And then lastly, h, I'm going to let that be the function e of f. Now notice I've written parentheses here for all my functions. So the right hand sides represent the specific arithmetic rule, if you will, for the function. And so this will allow me to utilize the formulation notation with for the derivatives, and I'll show that on the next slide. Now I am ready to apply the formulation for the derivative, reminding myself what I'm going to be expressing. So I want the f prime of the original function, and with the decomposition I've just shown, this is what the formulation will be. This is the Lagrange notation using primes. And so we can see readily that from our previous decomposition, this becomes easy to take derivatives. So we have g prime is equal to 3x squared plus 2. We have r prime, that's equal to 1/2 of the and then for f prime we have the derivative of the sine, which is cosine of r, and for h we have h prime, we have the derivative being just simply e to the f. Now notice, just for completeness sake, that what do we mean by g prime? Well, we mean g dg dx. What do we mean by r prime? Well, we mean dr dg. What do we mean by f prime? Well, we mean df dr. And what do we mean by h prime? We mean dh df. So these notations are all self-consistent, and that will allow us to use either prime notation or Leibniz notation. So if I put this all together, f prime I can express quite easily now just by substitution. So that I'm going to have e to the f times the cosine r times 1/2 g to the negative 1/2 power times 3x squared plus 2, and I can see from above I forgot to write what I had said. So at this point, what I can do is write this final result with the function being fully expressed in terms of x. So this looks like the exponential of the sine. So I'm going to write out all the pieces here. And because I'm doing this as a for the purposes of illustration, I'm not going to simplify this any further. I'll let you change the form if you desire. But this lets you see all the components of this new function called f prime with the original variable substituted back in. Next I will show this same result using the prime notation, the Leibniz notation. Now I'm ready to write the same result using Leibniz notation. In the Leibniz notation, we would have written the derivative in this fashion, df by dx, and with our decomposition formula, or a formula for the chain rule actually, we see that we have written this as dh df times df with respect to r dx. Now this enables us to see the chain pattern where the terms of the differentials appear juxtaposed to one another in the numerators and denominators. We've already computed these, and so without further explanation, I believe you can see at this point that this is what I've already had from the previous page, where the derivative of h with respect to f was written as e to the f times the derivative of f with respect to r was the cosine of r. Derivative of r with respect to g was 1/2 times the quantity g to the negative 1/2 power, and then finally the derivative of x cubed plus 2, which is 3x squared plus 2. Then finally substituting back all the original variable x, we clearly see that we have an equivalent result. And so I will just write that for completeness sake. And once again, I will let any further simplification be left to the observer. So times the quantity 3x squared plus 2. Okay, so this concludes an illustration of how to carry out the chain rule using either prime or Leibniz notation. So in summary, recognize that there are two steps required. One is to decompose the function into smaller or simpler pieces so that smaller derivatives can be obtained, or I should say simpler derivatives can be obtained, and simply substitute those in using the chain rule formula. I hope this little demonstration has been helpful.